Welcome. In this video, we're going to look into the differentiability of this function g, and g is the absolute value function. So let's begin with a review of what the absolute value function is. So that is g of x is equal to the absolute value of x. We can look at this as a piecewise function. It's equal to x if x is greater than or equal to 0. Otherwise, it's equal to negative x if x is less than 0. All right, let's look at the case where x is greater than or equal to 0. And we're going to choose h so that the absolute value of x plus h is just x plus h. So looking at this on a number line, if this is 0 and I know that x is larger than 0, we're taking our h to be small enough so that x plus h is still larger than 0. All right, now let's go ahead and apply the limit definition of the derivative. So g prime of x is equal to the limit as h approaches 0 of g of x plus h minus g of x over h. So this is the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x over h. Now, this is where this criteria we have here comes in handy. We know that that's going to be larger than 0. So this is the limit as h approaches 0 of x plus h minus x over h. Now, we began with the case that x is greater than 0, so it's absolute value. Now, continuing, this is just the limit as h approaches 0 of h over h, which is 1. Okay, now let's take a moment to look at the other case. That is the case where x is less than 0. All right, so x is less than 0, and we're going to choose x plus h again so that x plus h is still less than 0. And again, to see this on a number line, here's x, and we're picking our h small enough so that when we get to x plus h here, it's still less than 0. All right, so we can apply the limit definition again. G prime of x is equal to the limit as h approaches 0 of g of x plus h minus g of x over h. This is the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x over h. All right, so this is the limit as h approaches 0 of x plus h. And of course, since this is less than 0, based on our choice for h here, this is also less than 0. So that needs to be negative. And then I'm going to subtract the absolute value of x, which since x is less than 0, it's equal to negative x. And if you're struggling to see this, just think about the absolute value of, say, negative 2. We know it's positive 2, and that's equal to negative times negative 2. So it's negative x. And this is over h. So this becomes the limit as h approaches 0 of negative x minus h plus x over h. And this is just the limit as h approaches 0 of negative h over h, which is negative 1. All right, so here we are. If we apply the limit definition of the derivative for something for an x that's larger than h to this function, we get 1. And if we apply it to a value that's smaller than h, we get negative 1. Now, this tells me that g of x is not differentiable here at x equals 0 because its derivative is positive 1 when we're larger than 0, so here, and negative 1 when we're smaller than 0. Okay, so we know it's not differentiable at x equals 0. We've shown this using the limit definition. So now I want to wrap up just by looking at the graph of g and the graph of its derivative. Okay, so this is g of x equals the absolute value of x. Now, when x is greater than 0, we worked out that its derivative is equal to positive 1. Okay, and when x is less than 0, we realize that its derivative is equal to negative 1. Now, at 0, this is not differentiable because what's its derivative going to be? What, positive 1 or negative 1? So its graph will have these open dots here. The graph of the derivative, that is y equals g prime of x. Now, the key concept to take from this sketch is the idea that the absolute value of x is continuous. There is no discontinuity. The limit from the left and the limit from the right both equal 0 as you approach 0. And the function, the absolute value of x evaluated at 0, is also equal to the limit. So it's certainly continuous. It's defined, the limit exists, and it equals the value of the function here at 0. So this is certainly continuous. However, continuity clearly does not imply differentiability. So just because you have a function that is continuous does not necessarily mean it'll be differentiable.